Well, greetings, mathletes, and welcome back. Today's lecture is actually going to be, really, it's covering one result. And it's a pretty powerful result, but it's one particular limit that we're going to be after. And then we're going to take a look at a couple of examples and some of the consequences of that particular limit and what the result of that limit actually is. The limit we're looking for, that we're going to be taking a look at, is the limit. Oh, let's turn the pen on. The limit as theta approaches 0 of sine theta divided by theta. Now, if you look at that, it won't evaluate at 0, right? If you plug in 0, you get 0 over 0, and that's an indeterminate. What we are going to find is that the limit is actually 1, right? But we have to do some things to get there. One of the things we're going to be using is called the sandwich theorem. Which was actually covered in a previous section, but not in a previous lecture. I wanted to wait till we were actually using it for something important before we talked about it. Sometimes this is called the squeeze theorem. In fact, I might slip because I learned it as the squeeze theorem, although both names are completely fine. But here's the idea. If you have three functions and they have the relationship that f of x is less than or equal to g of x is less than or equal to h of x for every x. Now, that's a symbol you probably haven't seen before. The upside down A means for every, right? That's actually what it translates to, and that is a math symbol. That is not something I made up. It's just a little shorthand. It makes it a little bit easier to write some of this stuff down. And there's actually a little more. There's a little more to it right here. There's some conditions on X about having an open interval around that contains the limit, the point of the limit. But I'm not going to worry about that too much for the moment. This is the idea. If you can sandwich a function between two other functions, right? And the limit as x approaches some value of f of x is equal to the limit as x approaches the same value for h of x, right? And that's equal to some value L. Then, if I take the limit of g of x going to the same thing, I'm also going to get L, right? So this is the idea. Now, let me just kind of explain it to you with a picture here. Basically, what we're saying is if you have two functions graphed, you have one that goes up here, and you have another one that does something else. Oop, I didn't want that there like that. It's too close to not being a function. Okay. And they pinch off together somewhere, right? And you have some other function, g, right? So this would be f, and this would be h. These are your outside functions. And you have some other function, and this condition guarantees that g is between f and h. That means this can move around all at once, but when it gets to here, it's gonna have the same limit at that point, right? Because it's just kind of squeezed together there, right? And so this would be your point C where you're taking that limit. If the two functions come in and converge at that point C, then the one between them also has to converge to that at that point C, right, to the same limit. That's the idea of the squeeze theorem. Now, here's what we're going to be squeezing, because remember, we're looking at sine theta over theta, right? And so that's kind of a weird deal. I'm going to get some of this off of here before we start here, because we're going to need that space. Okay. So first off, let me show you what we're squeezing. Okay, so here's the idea. We're going to have, this is a triangle set onto the unit circle, right? So this is a circle of radius 1. So this is your unit circle from trig, really. This angle that it forms here is my theta, right? That's the angle. The first area we're going to find is this triangle here, right? The part that just got shaded, right? So we're going to be looking at this smaller triangle here, and we're going to find that area. The larger thing that the upper end that we're going to be looking at is this larger triangle here, right? So we're going to be finding the area of this triangle. Now, the thing that's in between them, and let's see if this works the way I think it's going to work. Let's see here. Is this sector. Now, a sector is like the pie slice from a pie, right? So the sector I'm looking for, whoa, that is not what I meant to happen. How did I do that? Oh, crap. Okay, so 3 failed attempts at that, and copy and paste works better. All right. So again, you saw the first triangle that we were looking at. That's this one right here, the one in yellow, right? It goes from here to here, across here. So you're looking for that. That's going to be the smaller one. And then the area of this triangle is going to be the largest function. And then the middle one, the one that's going to grant us what we want, is going to be the area of this sector here, the pie slice, right? Pizza slice, whatever you want to call it. Okay, so those are the three areas, and we have everything marked here. So that means the lower area is the area of triangle AOP. The sector here, right? We have sector AOP. It's the area of sector AOP. And then the last one is this triangle, AOT. Okay, so those are the three things that we're going to be looking for. So let's go ahead and compute the areas of each of these things one at a time. Remember, the area of a triangle is 1/2 the base times the height. Well, the base of all of these triangles is going to be 1, right? Because it's a unit circle. That's the base of both triangles that we're looking for on the outside. So the height of this thing is sine theta, right? And that's just from the unit circle. So that means that the area is sine theta over 2. Okay, so we got a sine theta in here. That's good. We started there. Now the area of the sector. Now you find the area of a sector if you have theta in radians. The area of a sector is theta over 2 pi, right? Because 2 pi is a full revolution. So this is the fraction of the circle it has times pi r squared. Well, the pi's cancel, right? And we know that r equals 1 because it's this right here. And so that means that the area of the sector is theta over 2. Well, that's nice. Okay, so there's a sine and there's a theta. Now we need the area of AOT. Now, you know, it's one of those things. I actually debated on explaining on how I wanted to explain that this is tangent. Now, in the traditional definition, the geometric definition of tangent, it's this side length, right? Just like the sine is this length and the cosine is this length here. This length is tangent, and it always is. But you can use similar triangles to verify that if you want. Remember, this side is 1, so that means that tangent theta over 1 is going to be sine theta over cosine theta, because this side's sine over cosine. And we already know sine theta over cosine theta is tangent, right? So this piece right here is the tangent, which means that 1/2 the base times the height is tangent theta over 2. This is why unit circles are nice. So first of all, I can multiply everyone by 2 and just get rid of the denominators. Right? Okay. We still don't have a ratio between sine theta and theta because this is what we're after. So what we're going to do is we're going to divide everyone by sine theta. Okay, so that puts this one equal to 1. That's nice. We have theta over sine theta here. And then over here, remember, tangent is sine over cosine, so the sines will cancel out. And, oops, not equal. This leaves me a 1 over cosine. And so the rules of inequalities basically say if you flip an inequality over, if you take reciprocals, you reverse the inequality. So that means that I have, well, the reciprocal of 1 is 1. I have my sine theta over theta. That's what I was after. And that's at cosine. Now, so this is the inequality I want. I have sine theta over theta squeezed now, right? It's been sandwiched between 1 and cosine theta. And so what I'm trying to find out now, since the limit of 1 as theta approaches 0 is equal to 1, right? Because that's true for any constant. The limit of cosine as theta approaches 1 is equal to 1. So both of the outsides go to 1 and the inside is trapped in there. These two things together imply that the limit of sine theta over theta as theta approaches 1, or excuse me, as theta approaches 0 is equal to 1. Now we had to do a lot of work for that. I'm not going to make you reproduce this entire proof. It's good that you've seen it at this point. We're going to be using it more later, and we will be using techniques like this later, particularly the squeeze theorem. But for this unit, we actually don't need to use the squeeze theorem any more than to get this particular result. And then we just need to walk through those results and try to understand what they mean, the consequences for our computations of limits. All right, so we have that. So we can just take this for granted now, right? Now that we've proven it, we're good to go. So let's go ahead and get rid of some of this other stuff. Just gonna Okay, I'm just gonna leave this up here because this is gonna be our foundational thing here. All right. Okay, so let's say we wanted to look at the limit as x approaches 0 of sine of the 5th root of 4x cubed divided by the 5th root of 4x cubed. Okay, now this doesn't, I mean, it looks similar to the sine theta over theta, but it's not quite the same. Now, here's how you tell if you can use this result. Okay, so what we want to check now is as if we let theta equal the argument of sine, right? Is it true that as x goes to 0, theta goes to 0? If it also goes to 0, right? So if I'm making x 0, theta has to be 0 too, right? That's basically what I'm checking. Is that as x gets closer to 0, theta does the same thing. As long as those things are interchangeable like that, you can do this. I can change this now. I'm going to let theta equal this. And if theta equals that, I can turn this into the limit as theta approaches 0 of sine theta over theta, which is 1. Right? So it makes some problems that look rather daunting move rather quickly, right? Okay, so now let's grab something that maybe doesn't have such an easy fix, takes a little bit more work to fix. So let's go ahead and delete that. And okay, let's say I want to look for the limit as x approaches 0 of sine 3y over 4y. Now you notice it doesn't quite match up, right? The argument of sine is not the denominator. So what we need to do is figure something out so that we can make the denominator a 3y. So if I just think about it a little bit, if I take 4 and I multiply it by 3/4, the 4's cancel and it makes it a 3. And I can multiply it by that as long as I multiply the numerator by the same number. So I'm going to do this. So this is now the limit as x approaches 0 of 3/4. Now I chose the fourths in the 4 in the denominator to cancel the 4 out here, right? So it's 3/4 times sine 3y over 3/4 times 4y. Well, this will cancel this out. And now what I have is the limit as x approaches 0 of 3/4 sine 3y over 3y. Well, with constants, right, I can take a constant and just pull it to the front as long as it's an actual factor. This is the same as 3/4 times the limit as x approaches, oh, I'm saying x and writing y. Doggone it, those are all y's. Ay. Let's just try that again. So the limit as y approaches 0 of sine 3y over 3y, which is 1. And so, excuse me, which makes this 3/4 times 1, right? Because it's 3/4, and this whole business right here is just 1. So that means that the answer is 3/4. Now, it's kind of interesting here because you notice the 3/4 here is right here as well. And the question probably pops up in your head, well, is that always the case? And these are exactly the types of things you want to be thinking as a mathematician. If you start to notice a pattern, see if you can generalize it and make it a result that you can use elsewhere. Okay, so we want to check to see if that's true now. So the question is it true that the limit as theta approaches 0 of sine A times theta over B times theta, is that equal to A over B? Right? That's our question. Well, it seems like, A and B could just be substituted in for 3 and 4, and then we follow the same steps. Right? So let's actually try that. Let's see if we can walk through the whole thing. I'm going to go ahead and get rid of all this stuff here, if I can. And we're going to see if we can walk through the same process again. Okay, so this time we're looking at the limit of sine A times theta over B times theta, and we're looking at this as theta approaches 0. Okay, so the first trick we used, we wanted this B to be an A. So for that to happen, what I need to multiply it by is A over B, right? And that cancels those things out. So that means I'm going to change this now to the limit as, let's try that again. The limit as theta approaches 0 of A over B sine A theta over A over B times B theta. Right? The B's cancel out, and so I have that A over B in the front. So A and B are constants, right? They're not variables, so that means you can just pull them out, pull them through the limit. So that gives me an A over B times the limit as theta goes to 0 of sine A theta over a theta, right? Which fits the condition of our original rule. The argument and the denominator match each other. And so this means that it's a over b times, well, this piece right here goes to 1. So this is just a over b. And so this thing is true, and we can use it in the future. So anytime we see a limit where the variable's going to 0 and it has this form, we can jump straight to the answer, right? This is the power of the mathematics, right? It's going to save us a lot of work. So that means that the limit as theta approaches 0 of, let's say, sine, 25 theta over 6 theta is just going to be 25 sixths, right? You can jump straight to the answer without doing computation this way. It's a very powerful result. Okay, so you have choices. You can either use the algebraic tricks, right, the arithmetic tricks to try to make that numerator and denominator match each time, or you can use this corollary to our theorem, right? Okay, so let's go ahead and take a look at another. There it is. Okay, so we have two results up here, both very useful results. All right, now let's look at another one. So let's say we have the limit as theta approaches 0 of sine 3 theta over sine 5 theta. Well, that's kind of interesting, isn't it? It's good, clean fun. These are the types of things, sometimes you have to poke around a little bit at these to get them to do what you want. So, but I have some tricks in mind. Okay, so here's how we're going to get a hold of this thing. We're going to start by separating these. This is now the limit as theta approaches 0 of sine 3 theta. I'm going to put it over 1, and then I'm putting some space on purpose here, times 1 over sine 5 theta. Okay, now this is one of those things where you ask yourself, well, what do I need here? Well, if I was going to do this, I'd want a 3 theta in the denominator down here, right, in this guy, and I'd want a 5 theta in this numerator. Those are the things I would want. So here's what I'm going to do. I'm going to multiply by 3 theta over 3 theta. And then over here, I'm going to multiply by 5 theta over 5 theta. Now, 3 theta over 3 theta is just 1. Right? It's just a 1. That's all it is. So it's not really changing anything. But now I can move this numerator and denominator around a little bit. Since all these denominators are being multiplied and all these numerators are being multiplied, I can move the factors around. And so that's what I'm going to do. I'm going to move this 3 theta into here, and I'm going to move one of these 5 thetas into here. So now this is the limit as theta approaches 0 of sine 3 theta over 3 theta. Oh, now I've just used this one, right? That's the one that's put in there. So this guy's still hanging out. And then over here, I have a 5 theta in the top. I'm not going to use this one on the bottom yet. I'm just going to write the sine 5 theta here. Okay, now we have to look at what's left. I put this one in the top here, and I put this one in the bottom. And so what I'm left with, I have this 3 theta over 5 theta left. So I'm going to write that in. Okay, now this is pretty common notation. When you have a product like this and you're taking a limit, you can take a limit of the products individually. And so quite commonly what happens is you draw an arrow through the term or through the factor, and then above it or below it write what the limit is. And so here, sine 3 theta over 3 theta, we already know is a 1. sine 5 theta divided by sine 5 theta would be the reciprocal of 1, which is also a 1. And then this one, I can cancel the thetas here. And so this is just times 3/5. There's no variable here, so I don't have to worry about the limit. And so what I end up with is 3/5 for that particular limit. And it's kind of interesting. Do you see the 3/5 up here? Right? I mean, it doesn't make, they don't seem like they should be related like that. There's nothing you could do to cancel these sines out or cancel these thetas out the way it's written up here. But at its limit, it does come down to 3/5. Now, it actually turns out that this is a more general result. Just like the last two, it turns out, oops, I wanted to switch that to blue, that the limit as theta approaches 0 of sine times a theta over sine times b theta is equal to a over b. And the proof actually follows exactly like this. We let 3 be a and 5 be b, and pretty much you can substitute directly in with those two values and work the same thing out generally. And so that's what I'm going to do. I'm going to go ahead and erase this, and we're going to take a look at it without the numbers and just with some generalized constants in there. We'll go from there. Okay, so let's go ahead and start with this limit. So we have the limit as theta goes to 0 of sine a x, oh, not x, almost did it again, sine a theta, it could be x though, as long as the limit, the variable of the limit is also x, over sine b theta. Okay, so if we remember what we did, we started by separating these. Right, we took the limit of theta as theta goes to 0 of sine a theta, theta over 1, and then I left a little space and I went 1 over sine b theta. Okay, now here, since I needed an a theta in the bottom, I put in an a theta. Right, and the same thing over here with b theta. Okay, from there, we rewrote the limit as sine a theta, right, over a theta, right? So that's using this one, putting it in there, times, and I'm going to take this one and put it in here, b theta over sine b theta, and then I was left with a theta over b theta, and the thetas can cancel here, right? And so again, just like before, this guy goes to 1, this guy goes to 1, and this guy goes to a over b. And so that means that our limit is a over b, right? And that's this result. Okay, so we've actually found quite a bit of stuff that's going to save us time here. So again, remember, you're always welcome to do it the long way, and it actually won't hurt you to do it the long way a couple of times before you start using the shortcut, just so you understand what you're doing in the shortcut, right? So it also allows you to understand when you can actually apply the shortcut and when you cannot. I do want to point out, because this is a fairly common place to mess up. If this limit here goes anywhere except to 0, right, it doesn't work, right? So that theta has to be going to 0 to use any of these results. Sometimes there's ways of massaging it so you can change the limits, but we haven't gotten there yet. So do remember that. Now, I want to go ahead and clear this off, and then we'll look at a couple more examples where this will just shorten our time quite a bit. Okay, so let me clear this off. Yeah, I'm just going to clear off everything. Okay, so let's suppose, you're walking down the street and someone jumps out from behind a dumpster and hands you this limit. Let's try that again. There we go. Let's say it's the limit as x goes to 0 of tangent 2x over x. Okay. Now, this doesn't look like anything we've seen so far. So our job is to try to make it look like something we've seen before. So there's a few things we can remember. I can, let's see, I can rewrite this. And keep in mind, I'm writing the limit every single time with every step. A lot of the time you massage the algebra and then just put the limit back in at the end. Remember, tangent is sine over cosine. So this is now sine 2x over cosine 2x times 1 over x, right? So we can separate the functions out. Well, let's see here. This is multiplication, so I can just swap these. This is now the limit as x approaches 0 of sine 2x over x times 1 over cosine 2x. Well, remember our result. If I have the limit as theta goes to 0 of sine a theta over b theta, I get a over b, right? Well, in this case, b is 1. So that means that the limit of this factor goes to 2. Well, cosine's not 0 at 1, right? So this ends up, oh, I'm sorry, at 1. Excuse me, at 0. I'm plugging in 0 for x. So cosine of 0 is 1. That's what I was trying to look at. So this ends up being a 1 over 1. So this goes to 1. And so that means that the limit is 2. So the limit of tangent 2x over x is equal to 2. Now there's a little hint in here that maybe tangent ax over bx ends up coming out to a over b. So that might be something you want to explore just to see in general. Is it true that the limit as theta goes to 0 of tangent x over x, or actually, let's generalize it more, tangent ax over bx, we don't know, is that equal to a over b every time? It's a good question. I'm not going to answer that question right now. You guys can you can work that out. It'll save you a lot of time if it turns out to be true. Keep in mind, it may not be true. It may be one of those things that's only true in this particular case that we just saw. So, it might be something to think about. Okay, now let's see here. So let's look at another one. Let's go ahead and clear that one off. All right, so the next one I want to look at here is going to be I keep forgetting to turn my pen back on. Okay, is going to be the limit as theta goes to 0 of 1 minus cosine theta over sine 2 theta. Now, I want to say a couple of things about this. I'm going straight to the solution, but I poked around with this one for a little while, just trying a few different things to see what would work, because I knew a general method that would work, but I wanted to see some of the other things that you guys might try. So, thinking about that, one of the things that I had done is I split it up over the numerator. So I had a 1 over 2, 1 over sine 2 theta minus cosine theta over sine 2 theta, and I couldn't get anywhere with that. I tried a few different things. So keep in mind that you don't generally go straight to the solution with these types of problems, because this is going to require a trig substitution. And sometimes you don't make the right substitution the first time. If you guys remember going through your trig identities and trying to prove identities and stuff, you remember that big circle you'd end up working in, and you end up back where you started. So these can be frustrating. So be patient with yourself as you're working through these. But excuse me, what I ended up settling on was one of the half angle identities basically says that sine squared of x is equal to 1 minus cosine 2x over 2. Right? That's one of your half angle identities. And so that's why it's a really good idea to have, a sheet of identities with you, even if you haven't memorized. Oftentimes just having it there helps you remember things that maybe wouldn't pop into your mind otherwise. In any case, I don't have a sine 2x. That's interesting, but there's a 1 minus cosine, and I have a 1 minus cosine here. Okay, so here's what I'm going to do. I'm going to move this 2 over. Oops. Try it again. 1 minus cosine 2x. And I'm going to I need a cosine theta. So what I'm going to do is I'm going to let 2x equal theta. And since I have an x over here, if I divide over, right, that means x is equal to theta over 2. So I can make substitutions now. This is now 2 sine squared theta over 2. Oh, I shouldn't have written it there. Let me drop it down a little bit. So this side comes down to 2 sine squared theta over 2. And then this side is 1 minus, 2x is equal to theta, 1 minus cosine theta. And that's the piece that matches. So I can make that substitution now. Notice I had to do a little bit of algebra to make it fit. Then we have the limit as theta goes to 0. And I'm not using 1 minus cosine theta anymore. It is now 2 sine squared theta over 2 divided by sine 2 theta. Well, interesting. Now, if you think about the results that we do have something that has a sine over a sine. Sine ax over sine bx. When I take that limit, when x goes to 0, I get a over b. So if we split up this square, I can actually rewrite it this way. In fact, I'm going to put the 2 out here because we don't have to think about it until the end. So I'm going to take this and put it out in front. And so this is now sine theta over 2. I'm going to put times sine theta over 2, right? So I'm splitting up the square. And then I can just put the sine 2 theta here. Well, this helps us quite a bit. This now, if I look at it, is sine 1/2 theta, and this is sine 2 theta times sine theta over 2. Okay, well, that makes this my A and this my B. So that means that this simplifies to 1/2 divided by 2. 1/2 divided by 2. Well, sine is continuous at theta, right? There's actually a value there. If I plug in 0 into this, sine of 0 is 0. So this is times 0. This piece goes to 0. And then over here, I still have my 2 out in front. But none of this other stuff matters because I have a times 0. So this limit is 0. But you notice how I took it and I massaged it until it fit one of my results, so I could reuse what I had already found. Right? You can see how painful this would be to compute just this. If I just needed to compute this by itself first, that would be a whole nother set of algebra. But because I have that little corollary that I found, I can shorten things up quite a bit. All right. Now, where's that button? There it is. Okay, so that's the main stuff I wanted to go through today. Now, there is going to be some more. There's a second half to this particular section. Um, and the second half isn't quite as intense as this half. This was the more heavy algebra. The second half is more about interpreting the pictures of graphs and interpreting things like that, kind of like we did in the last section we were talking about limits. So that one's not as bad. I wanted you to have a little more time to cogitate on this before next week, because exam and all that. So, in any case, that concludes our lecture. And so, until next time, keep your pencils and your wits sharp.